moving on. So the last thing we're going to talk about now, the final thing, real gases. So this whole time I've been kind of describing the properties of ideal gases. So remember, they don't occupy any volume. They don't interact with each other, okay? However, in reality, gases do have volume, and they do interact with each other. And so the ideal gas equation can be modified for what's called the van der Waals equation. You don't have to have this memorized, and I think I'm only going to ask you to do it like one time in the book, in the homeworks, okay? But what I want to show you is the ideal gas equation, it gets modified to account for these things, for the fact that the gases have volume and they do interact with each other. And I'm going to show you how. It's pretty cool. So we can see here PV equals nRT. And then look, check it out. All of this junk equals nRT. Okay? So we're good there. We've got this side of the equation and this side of the equation. So no explanation necessary there. So now what about these other things? Well, check it out. I'm going to underline the P. Okay? And I'll point out to this whole chunk, right? And now I'm going to grab a different color, and I'll point to the V, and I'll underline this whole chunk, okay? So these are the two ways in which pressure and volume get corrected for these being real gases. For one, we note that this V and this V is the same, okay? But what's this NB term? Well, as it turns out, this term, N times B, that's number of moles, and B is the molar volume constant for the molecules themselves. So this NB chunk represents, I'm going to just say, volume of molecules themselves, okay? And so notice that it's being subtracted from what I'll call volume of the container that's holding those molecules, okay? Because those molecules occupy real space, we have to subtract that real space out of the volume of our container to really conceptually have, or not conceptually, but quantitatively have a correct determination of volume. Okay, what's all this stuff? Okay, well, the observed pressure is what you would measure, okay? And this whole chunk of this thing right here, A times N, and that's moles, and that's V for volume, okay? Squared, this chunk represents the collisions of molecules with themselves. So in other words, this P observed, that's really the collisions with the wall, with the container. And then this chunk right here are the collisions with the molecules themselves. So really these equations are actually quite similar. They just have these correction terms, okay? And I like to play this thought experiment. Oops, we'll play the thought experiment next. What I want to show you now, the result, if we take the equation and play with this here. So remember, PV equals nRT is ideal gas equation. If I divide both sides of this equation by nRT, let's do that. Divide this by nRT and divide this by nRT. Then I get PV divided by nRT equals 1, right? And so if I were to then plug in what I would actually measure. So keep in mind, right, the ideal gas equation, it's just an equation. It doesn't necessarily give us the correct pressure that we would actually measure, okay? So this PV divided by nRT equals 1, that's the ideal gas line. And look, here that line actually is, okay? But now look what happens. So here for nitrogen, methane, hydrogen, carbon dioxide, if we were to actually make measurements of the pressure and then plug it back into this equation, look what happens. They don't actually hover over hover through this line. Okay? And, 1,000 atmospheres, I want you to really have this impression. 1,000 atmospheres is crazy. You could make a diamond with 1,000 atmospheres out of a piece of graphite. I mean, that is insane pressure, okay? The pressures that we deal with in our atmosphere, like I'm gonna make a red box around it, okay? Like a tiny little red box right there, and I'll say like, this red box represents us at sea level. So in other words, in most cases, all of these gases behave ideally. Like if you zoom way in, you see they're all around that 1.0 mark. Okay? So at sea level, these things are always behaving ideally. But you notice when you go to really humongous pressures, they're not so ideal anymore. And that's what I kind of talked about at this very beginning slide. Yes, that a low pressure sample is fairly ideal. A high pressure sample is not ideal. Well, as it turns out, low pressure is about atmospheric pressure and lower. Okay? So in the grand scheme of things, in the grand universal scale, all right, atmospheric pressure on planet Earth is fairly low in the grand scheme of things. Okay? So this high pressure sample would have to be much, much greater than atmospheric pressure. Okay? And so obviously out in space, gases behave extremely ideal. They're very ideal in space. Okay? It's these really high pressure situations where gases do not behave ideally. So now what about temperature? Okay, so now this graph is still the same situation, PV divided by nRT. The 1.0 line is the ideal line. And now this is the same gas, but at different temperatures. And check it out, 293, that's about room temperature. And if you follow this curve here, and I draw a box around this once again, you'll notice that the black curve, this 293 curve, right, it's hanging around that ideal gas line very well, okay? But when you get outside of that temperature range, either lower than 293 or greater than 293, that really changes the way in which gases also behave ideally. So really this ideal gas range, it's kind of a coincidence that ideal gases are occurring around Earth conditions, okay? So ideal gases are really like planet Earth conditions, okay? And that's because under these conditions, this is where we figured out all these laws, right? The people who were measuring pressure and volume and temperature of these gases, they weren't doing this in space. They weren't doing this in these crazy pressure chambers. They were doing it in their labs that were approximately at sea level and room temperature, okay? So it just so happens that ideal gases behave ideally under these planet Earth conditions, okay? But much outside of those conditions, gases behave real, like non-ideal gases. And so what that means is you have to use this equation for non-ideal behavior. You use this equation for ideal behavior. And so you can certainly use the non-ideal gas equation whenever you want, that's fine. You just get an extremely accurate answer. And that answer, if it's under ideal conditions, will be extremely similar to what you get for the ideal gas law, okay? So now